Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So Anupam was once at Stanford, but has been at CMU now for 6 years? 5 years, and has done a lot of interesting work both on verifying the correctness of various cryptographic protocols, and more recently on looking at various aspects of privacy, from differential privacy to private audit logs, and trying to apply a lot of rigor to a difficult area, in addition to understanding things like the HIPAA laws, which has its own fun and challenges there. So today he's going to talk a little bit about the audit piece.
All right. Thank you very much, Brian, and thank you all for coming. I want to summarize some work that we have been doing over the last 5 years or so at CMU on trying to understand privacy at a more semantic level so that it's more clear what privacy policies actually mean operationally. And it has led us to mechanisms based on audit and accountability for enforcement. And just to place things in perspective, we now live in a world where personal information is everywhere. Information about individuals is collected through search engines and social networks and online retail stores and cell phones and so forth. And all this information is being collected by these, in many cases, by companies which now hold vast repositories of personal information. So this raises a basic question, a privacy problem. How can we ensure that these organizations that collect these vast repositories of personal information actually respect privacy expectations in the collection, disclosure, and use of personal information? Now, one approach that has evolved in practice is that we are beginning to see emergence of more and more privacy laws in various sectors, as well as privacy promises that companies make, like Microsoft and Google and other companies that hold personal information, about conditions under which information will be collected and used and shared. Just to make things a little more concrete, here are some snippets from the HIPAA privacy rule for healthcare organization that gives you a sense of the kind of examples of policies that exist in this space. So here's one example that says a covered entity, that's a hospital or a healthcare organization, is permitted to use and disclose protected health information without an individual's authorization for treatment, payment, and healthcare. Here's another that says that a covered entity must obtain an authorization for any disclosure or use of psychotherapy notes. So in general, for personal health information, so long as the information is being shared for these purposes, there is no need to get authorization from the patient, except for the special case of psychotherapy notes. And these are just two snippets in a large and complicated law that includes over 80 other clauses. It's the kind of thing that is going to be extremely tedious to enforce manually. So we would like some algorithmic support in enforcement of these kinds of policies. And there are many other laws. This is just one example. There's the Gramm-Leach-Bliley Act that financial institutions have to comply with. There is FERPA for educational institutions in the US, the EU Data Privacy Directive, and so forth.
I have a question.
Yes.
Concerning the first 2 points.
Okay.
You somehow implicitly assume that deny overrides permit.
So the way the law is written, I have not shown you the entire piece, but it uses mechanisms like exceptions. So the way it says is that this is the clause, except if, and then this. And so the priority, if you will, what clause preempts what other, is encoded into the law using this exception mechanism. And that has a natural logic, that leads to a natural logical presentation of the law also. Now, so those are some examples of the kind of policies we see in regulated sectors like healthcare, but on the web also, companies make promises in their privacy policies that they are expected to respect. Otherwise, the FTC can and has impose fines on them and such. So So here's some examples. So Yahoo's practice is not to use the content of messages for marketing purposes, and then there's something from Google's policy here. Now, it's one thing to have laws and promises, but the question is really, are these promises actually being kept, right? Or are these laws actually being complied with? And there's a lot of evidence that we have lots and lots of violations of the kinds of clauses that appear in these laws. So there are examples of healthcare, in the healthcare sector, breaches and violations of HIPAA. This was an example of where Facebook was called, had to pay a price for not living up to their promises. Google ran into rough waters and so forth. And this Wall Street Journal selection, series of lectures on, a series of articles on what they know, what they call the What They Know series, has lots and lots of such episodes about where privacy promises are not being respected or the practices are somewhat questionable. So that's the broader context, but the technical question that I and others are interested in is what can we as computer scientists do to help address this problem. So let me focus on a very concrete scenario and a snippet of a privacy policy from HIPAA to motivate some of the technical questions that I'll get into later in the talk. So we'll consider a simple scenario from healthcare privacy where a patient comes and shares his personal health information with a hospital. The hospital might use this information both internally for purposes like treatment and payment and operations, and share this information with third parties like an insurance company for the purpose of, say, in this case, payment. But when this information flows in a manner that's not permitted, for example, if this information goes out to a drug company, which is then used for advertising, then that would be a violation, right? And in addition to this cross-organizational flows inside the hospital also, there's a complex process, and there could be violations internally also where information is used in inappropriate ways. Now I guess the one thing I want to point out here is that many of these violations are going to happen because of authorized insiders. People who have been given access to this information for certain purposes, like treatment and payment and operations, but then they either use that information in ways that are not permitted or share it under conditions that are not permitted. So we do not expect that the problem will be solved using well-known techniques from access control, which is because the people who have a legitimate reason for access are exactly the ones who are committing the violations. So access control is, of course, necessary in this setting to ensure that employees, people who are not employees of the hospital do not get access to the information, but that is not going to be sufficient for enforcing the kind of policies that appear in this application domain. So let's look now at a very concrete example from the HIPAA privacy rule. And it's going to be a bit of a mouthful, but the reason I picked this particular clause from HIPAA is that all the concepts that are relevant in a whole bunch of privacy policies, including HIPAA and a lot of other policies, show up in this one example. So the policy says that a covered entity, again, think of that as a hospital, may disclose an individual's protected health information to law enforcement officials for the purpose of identifying an individual if the individual made a statement admitting participating in a violent crime that the covered entity believes may have caused serious physical harm to the victim. Right? So it's a very long and convoluted sentence, but let's look at the different pieces and the corresponding formal concepts that they represent. So first of all, when we talk about privacy policies, there's often going to be an action involving personal information. So in this setting, in this example, the action is a transmission or send action that goes from a sender P1 to a recipient P2, and it contains the message M. In this example, the sender P1 is the hospital, the covered entity. P2 is the law enforcement official, and M is the message that contains the information that is being shared. But in addition to transmission actions, there could be accesses or use actions, other kinds of actions that involve this personal information. The second piece is that this is common in HIPAA and many other privacy policies. In order to get some abstraction, often roles are used to group large classes of individuals. So in this case, the recipient of the message is in the role of law enforcement. And the same policy will apply to all law enforcement officials, not just to P2. There are data attributes of the message that is being transmitted. So in this clause applies to messages that are of the type protected health information. And you could imagine a characterization, an attribute hierarchy, if you will, that says that various types of information are protected health information. So a prescription might be protected health information, whereas maybe a email that contains some scheduling, appointment scheduling is not. Right? Then there are these temporal concepts. In this case, the policy permits the flow of information if in the past a statement was made to this effect. And temporal concepts capture a bunch of privacy idioms. For example, often in privacy policies, you see things like consent. So if in the past a customer or patient gave consent, then it was okay to share information. There are also things like notification that require bounded future temporal constraints. So notification policies are of the form that if any organization loses their personal health information or personal information about customers, then within a certain number of days, like 30 days, they have to inform the customers that they have lost their information. So that's a bounded future requirement. So temporal constraints about the past and bounded future, timed temporal constraints, are going to show up a lot in these kinds of privacy policies. Now, in addition to these concepts, now we will begin to see some other grayer concepts that are also somewhat vaguer, right? So in particular, there is this notion of a purpose, which shows up all over the place in privacy policies, right? So in this case, the disclosure is permitted for the purpose of identifying criminal activity. In many cases, you'll see companies promise that information will be used for one purpose, say to improve the search experience or to improve treatment, but not for other purposes like marketing and so forth, right? So that raises a basic question. What does it mean for an action to be for a purpose or information to be used only for a purpose or not for a purpose? And what does that mean semantically, and how would we enforce these kinds of promises or policies? Another thing that shows up is beliefs. So you see here, in this example, there is this notion that it's okay to do the disclosure if the hospital believes that the crime caused serious harm. So this requires some understanding of beliefs. Now I'm going to separate out these two classes of concepts into what I'm going to call black and white concepts. These are things for which semantics are not that hard to give based on previous work on giving semantics to policies and enforcement techniques. The enforcement will be difficult for some other reasons that I'll explain. And these are much more vague. In purposes in particular is one thing that we are going to focus on. Beliefs, I'm not going to talk about too much today, partly because I believe that a lot of the work that has been done on authorization logics could directly apply to the belief part of this. So we are going to not deal with beliefs, appealing to prior work, but I do want to highlight these two broad classes of concepts that arise in privacy policies, and I'm going to discuss some methods for their enforcement. So very broadly, the 10,000-foot view here is that there's a research area to be explored in formalizing privacy policies, giving precise semantics to various privacy concepts and their enforcement. And in enforcement, I'll talk about at least two classes of techniques. One, to detect violations of policy. In some cases, as we'll see, it'll be very hard to prevent violations. And also accountability, where by accountability I mean that when a violation is detected in a multi-agent system where many people could have done many different things that could ultimately led to the violation, how do we identify agents to blame for policy violations as well as incentives to deter policy violations. So much of this is work in progress. I'm going to focus primarily on the audit piece today. So at a very high level, one way to think about this is this parallels how the justice system works in practice, where there is a law, but the enforcement is not always based on prevention. It requires police officers to do detection of violations and give parking tickets and other mechanisms for assigning blame and appropriate punishments. And that's what we are going to try and mirror in the digital world. And detection will be the first step of that process. Now, we are not the only one to talk about the importance of audit and accountability in this setting. There have been a couple of recent position papers from MIT, from Hal Abelson, Danny Weisner, and others, and also Butler Lampson. And in fact, there is also in the corporate world, there is increasing push for accountability-based privacy governance, in which Microsoft, the corporate privacy people at Microsoft, have been largely involved. The goal, one big goal of this work is, suppose that there is a regulation or that organizations are expected to comply with. How do they demonstrate to a third party that in fact they are complying with these regulations? And so far, much of this has been very ad hoc, but part of what I'm going to talk about today is a step towards producing algorithmic support for these kinds of tasks. So at a very high level, the approach for audit is going to parallel the separation between the black and white concepts and the gray concepts. So we start off with the privacy policy and put it into a computer-readable form. And we have actually done complete formalizations of both the HIPAA privacy rule and the Gramm-Leach-Bliley Act for financial institutions. And one way to think about this audit box is that it takes as input an organizational audit log that records what software systems and people have touched what pieces of data or shared what pieces of information, and the policy. And then the audit box comes back with, well, this policy was violated on this execution. That kind of information, whether a violation happened or not. And paralleling the informal separation that I mentioned when I walked through the policy example, we have one algorithm that does fully automated audit for these black and white concepts, and a different algorithm, you can think of that as an oracle that provides guidance on these gray policy concepts. So the second algorithm is going to be a little tricky to get at, because it's trying to, in particular, it focuses on this purpose piece. And the reason it's complicated is that we are trying to figure out whether a person accessed information with thinking about achieving a purpose like treatment or not. It's as if we are trying to understand the human psyche, right? We are not there yet. We don't have the oracle from the matrix yet, but we'll try to approximate it using some AI techniques. So those are the two big pieces of the technical presentation. So let me first talk about auditing black and white policy concepts, and this is joint work with two of my postdocs, former postdocs. Deepak is now a faculty at Max Planck, and Lim Geo, who's still at CMU. So in order to audit these black and white concepts, although I said they're somewhat simpler than the gray concepts, there are still two main technical challenges. One challenge is that these audit logs are incomplete, in the sense that they may not have sufficient information to decide whether a policy is true or false. So if you think about access control, let's say file system access control, when I try to read the file, there is a reference monitor that's sitting, and it'll either let me access the file or not, depending on what the policy says. So there is often in access control, there's enough information to decide whether to allow access or not. So the reference monitor will come back with a yes or no answer. We'll see that in the presence of incomplete audit logs, we will not always get a yes/no answer. It could be that the parallel of the reference monitored, this audit algorithm can either say, yes, the policy was satisfied, no, the policy was violated, or it can say, I don't know. But we want to deal with the I don't know scenario in a graceful manner. So there are a bunch of sources of incompleteness. One is future incompleteness. So since we might have these notification-like laws that talk about what needs to happen in the future, there may not be enough information in the log at the current moment to say whether it's violated or not. But the hope is that as the log grows over time, we will get to a point where we will know for sure. There may not be information about some of these gray concepts, these somewhat subjective concepts. There may not be, evidence may not be recorded for purposes and beliefs and things of that nature. Sometimes logs may be spatially distributed, and there may not be information in one log to decide whether the policy is violated or not. So we are going to, yeah.
Can't keeping a log violate some of these policies?
Can what?
Can't keeping a log violate some of these policies?
Good. Yes, it could. This is the class of policies that I'm enforcing here, primarily policies that will talk about conditions under which information can be shared or not, or used for a certain purpose or not. We don't have mechanisms to deal with, say, data retention policies and things like that. They have to be dealt with using other mechanisms.
But I mean, who has access? The log is operating on human subjects data, and did all of the people who contributed to this system with data consent that their medical records would create records in a log, which then you would access and do studies on?
That's an interesting point. So under law, HIPAA requires these healthcare organizations to maintain these audit logs. So healthcare organizations have to maintain these audit logs. And then there is often, the way it works in practice, so I should say that there are audit tools that are now appearing in the market for healthcare audits that are getting bought and used. Often the way that they're getting used is that there are some designated people in the audit office, if you will, who access these logs. And these existing commercial tools do very simple things. You can only issue SQL queries. So you can check find all employees who accessed more than 100 times in the last 2 days. Things of that nature, right? And then the audit, these tools, there is the Fair Warning tool, and then which is a startup that is doing reasonably well. The other tool, the P2P Sentinel tool, which is acquired by Cerner, does the similar thing. What they also do in addition, which is partly maybe what you're getting at, is that they also keep track of who accessed the audit log. So there's another layer of, but that's about as far as there is a trail of who is accessing the audit log information.
Right, but you said they're required to keep the audit log.
Yes.
But the moment a researcher goes in and does research using the audit log, that's different than keeping the audit log.
The researcher going in, so HIPAA allows, I'm not particularly happy about this clause in HIPAA, but HIPAA allows de-identified. So we have not done any study. If you're asking me whether I have looked at these logs, the answer is no. But if you're asking whether it is permitted under law, the answer is yes. HIPAA allows de-identified for a very operational notion of de-identified, but that may be very unrelated to protecting privacy. It allows de-identified information to be shared for the purpose of research. Right? So under HIPAA, it's permitted. You don't need consent from patients to do that. All right, so this is one big challenge, the dealing with incompleteness. And the way we are going to do that is a very simple idea. We are going to model these incomplete logs uniformly as 3-valued structures, meaning that given a predicate, the log might tell us that the predicate is true or false or unknown, meaning that it doesn't know, doesn't have enough information.
Somehow, implicitly, it seems there is a presumption that things are consistent, because in addition to this fourth category.
You mean the policy?
The policy
yes.
is inconsistent.
The policy we are assuming is, if the policy is inconsistent, then all bets are off because false will imply nothing. So we haven't found, it's a good question. We haven't found any inconsistencies in HIPAA. And part of the reason for that, HIPAA is very largely operational. So that was a good thing. That's part of the reason why we looked at that. But part of the reason for that is inconsistencies might arise when one part of the policy says do something and another part says don't do it. But whenever that has arisen in HIPAA, it has always come through this exception mechanism so that it's clear what overrides what. Now, we haven't done a mechanical automated analysis to check for consistency, but maybe that's something we can do because now we have it in a machine readable formalization.
For the log,
yes.
Assuming they're all, like if you're pulling lots of different logs together, you're assuming that they're all consistent, you just might be missing some pieces.
It might be missing pieces. That's incompleteness. Incompleteness we can deal with. Inconsistency in the logs will also be problematic for the same reason, because we are assuming that if a predicate is true, then it cannot be false. But the logs are not necessarily pulled from different places. So the application we are going to do with the real logs, which has taken like more than a year to get close to it, is from the Northwestern Memorial Hospital, which is part of the SHARPS project that I'm on. Carl Gunter has already done some experiments and published results on that. It's one place. It's like a Cerner log that it's not a distributed log. Right. So it's a very simple abstraction. Given a predicate, the log will tell us whether it's true or false or unknown. Right? And then the meaning of larger policy formulas can be defined using this three-valued logic. Now, the idea of this iterative reduce algorithm, which is the audit algorithm, is that it takes a log in a policy, but unlike standard access control or runtime monitoring, instead of coming back with a true-false answer, it'll check as much of the policy as it possibly can, given the information in the log, and output a residual policy, which will contain only those predicates for which the log says unknown. I don't know whether it's true or false. Right? So that'll be a simpler policy. And then when the log is extended with additional information, you can run the algorithm again, and you proceed in this way iteratively. Right? So pictorially, you have the log in the policy. Think of this phi0 as HIPAA. You run reduce, you get the residual policy phi1. When the log it grows, there's potentially more information now about the predicates in phi1 that there wasn't information about here. You run this again, and this process continues. And at any intermediate point, we can invoke the oracles for the gray concepts. Like if we have an algorithm for determining purpose restrictions, then you can call that algorithm, because this algorithm is not going to deal with those gray concepts. Right? So that's the picture. So in a little bit more detail, the policy logic looks a little bit like this. I don't want you to try and read everything on this slide. It's a fragment of first-order logic. We need over unbounded domains. But the interesting technical challenge here is that we have to allow for quantification over infinite domains, because HIPAA talks about for all messages. The messages sent out by the hospital has to respect some policies. And because of that, that's the technical challenge where we have to go beyond what is already known in runtime monitoring. And the logic is expressive. Since it has quantification over these infinite domains, you can quantify over time, so you can express timed temporal properties. Now, if I take this policy and write it out in this logic, it looks a little bit like this. Again, I don't want you to necessarily read the formula. The important thing here is that there is going to be a distinction. Well, there's quantification over all messages. The set of messages in English is infinite. And all time points. And the other thing to take away is that there are these the black part of the policy, which the algorithm will deal with automatically. And then there are the red parts, which are really the gray concepts. And this algorithm will not deal with. So it talks about things like purposes and beliefs and so forth. Right? Now, the formal definition of the reduce algorithm, let me show you little snippets of it. If the formula is just a predicate, then the algorithm will find out from the log whether that predicate is true or false or unknown. If it's true, it returns true. If it's false, it returns false. But if it's unknown, then it returns the whole predicate P. So in this case, the residual formula is the entire predicate P, right? And then we do apply this recursively. So if it's a conjunction, you just apply reduce on the two parts and so forth. The interesting case is when we have universal quantification over an infinite domain. Now, one naive way to try and do this is to consider all substitutions for x. And then this becomes a conjunction, so phi with x set to x1 and phi with x set to x. But that's going to be an infinite formula, and obviously the algorithm will never terminate if you do that. Instead, we are going to restrict the syntax to have these guards. So since this is an implication, it's going to be trivially true when C is false. The interesting case is when C is true. Now the C will be such that there's only going to be a finite number of satisfying substitutions of x, and that finite substitutions can be computed. So intuitively, one way to think about this is, if you think about HIPAA, then what is HIPAA saying? HIPAA is saying that every message sent out by the hospital should respect some complicated logical formula that represents HIPAA. But the number of messages sent out by the hospital is finite. The hospital does not send out every possible message in the English language. There are only maybe a few messages that the hospital sent out to third parties. So for this predicate is going to be true only for those messages. And in that case, you get this as a finite, the instances you'll get as a finite conjunction, right? So and when we write this out in Greek font, then you get one conjunct for each of the finite substitutions that makes C true. And then the rest, this is saying, allowing for the incompleteness in the audit log. Since in the future, you might get other substitutions, more messages might get sent out, or even the log was not passed complete. So maybe there were some messages that will show up as the log expands. We have to somehow deal with that, and that's captured by this conjunct, which is saying if I get other substitutions other than the ones that I've already considered, then I should also have a piece for that in the formula. Yeah.
If I understand correctly, you say that in HIPAA, it is always the case that appropriate guard, finitizing guard, can be found.
That's right. That's right.
So why would it have not been acceptable to convert for all must into none may?
For all must.
So the audit requirement being that there is no message sent by the organization that violates the rule, rather than all of them must follow the rule?
So that's fine. That doesn't change anything, right? So if I express that, well, if I express that in this first order logic, that's an existential quantifier over an infinite domain, and that'll become an infinite disjunction. Converting universal to existential will not help. Well, maybe we can take that offline. Right. So I guess coming back to your question, the general theorem though we have is that if this initial policy satisfies a syntactic mode check, where we're using the idea of mode checking from logic programming, then the finite substitutions can be computed. So this general theorem now applies. So we now have a syntactic characterization of these guards, for which the finite substitutions can always be computed. And it turns out that as an instance of that, we get the whole of HIPAA and the whole of Graham-Leach-Bliley. So if someone comes up with a third law that we want to look at, then we would like to see first whether this theorem applies to that law or not. If it does, so the generality has that nice property. And our argument for why this somewhat esoteric theorem that uses techniques from mode checking is useful in this setting is that, look, the whole of HIPAA and Graham-Leach-Bliley actually satisfies this test, right? So if you look at this particular, going back to our policy example, and here's an example of an incomplete audit log. Now, if you look at all those quantifiers, then we are going to find substitutions for the variables P1 and P2 and M and so forth by mining this log. So mining this log, you see that the send predicate there's only one instance of send, that's this instance over here, and that'll give us the substitution that P1 corresponds to UPMC and P2 corresponds to the Allegheny police, and that message M corresponds to exactly this message M2, and so forth. So we can mine these from the log, and when you do that, now we know the truth values for various predicates, and we are left with a residual formula that only contains the gray part of the policy. The rest all become true and disappear. And we have actually implemented this and applied it to simulated audit logs. So this is not our real audit logs. We haven't gotten our hands on audit logs, on hospital audit logs yet when we wrote this paper for CCS last year. And it turns out that the average time for checking compliance of each disclosure of protected health information is about 0.12 seconds for a 15 megabyte log. So this does scale reasonably well. Now, so that's performance. So one thing to be careful about for performance is that as you apply this algorithm, the residual formula can actually grow because we have the finite substitute, whenever we see a for all, it becomes bigger because you get one entry for each of the substitutions that you mine from the log, and then there is the residual piece. So after a few iterations, the policy will become too big for the algorithm to work, because the residual formula largely has these things like purposes and such, which this algorithm cannot handle. And that's something how to handle purpose is the next part of this talk. The other thing that is a relevant question for this application is, reduce can only deal with what I'm calling black and white concepts. Everything else shows up in the residual formula. In HIPAA, about 80% of all the atomic predicates is actually what I'm calling black and white, which means that the algorithm can deal with that completely automatically. So that doesn't mean that 80% of the clauses of HIPAA are black and white, though, right? So I'm just counting the number of atomic predicates. Now, in HIPAA, there are about 85 clauses, of which about 17, which is 20%, is completely black and white. So for those 20% of the clauses, this algorithm will be fully automated. And for the others, there are things like purposes and beliefs that we have to deal with. So purpose remains an important problem, and that gives us a sense of purpose. Now, in terms of related work, there has been a fair amount of work on specification languages and logics for privacy policies. Some of them are either not expressive enough to doesn't have the richness to capture this kind of policies, or they are not designed for enforcement. Like P3P is primarily a specification language, not a mechanism for enforcement. And our prior work, so this was work I did back at Stanford, we used quantifiers for specification, but the enforcement was really using propositional logic. So we couldn't enforce the whole of HIPAA using that prior work. In terms of actual specification of laws, we had looked at a few clauses in this earlier work, and Gunter looked at one section, and some work at Stanford from John Mitchell's group looked at a few more sections, but our work is the first that does the whole of HIPAA. The nearest technical work in terms of monitoring, runtime monitoring, is this work from David Bazin's group. They have a much more comprehensive implementation and evaluation. They have actually applied it to real audit logs from Nokia, which we are also trying to get now. And they seem to work quite well. The two things that make that approach unsuitable for this application is, one, they also have a kind of mode checking, which they don't call mode checking, but they call it a safe range check. But that is a much less expressive way of restricting the guards. And in fact, this restriction is too restrictive. It cannot express the kind of clauses we see in HIPAA and GLBA. The other thing is that, like much of the work in runtime monitoring, they assume that audit logs the executions are past complete. So the only source of incompleteness is future incompleteness. And that's also something that we wanted to avoid and be more general about allowing other forms of incompleteness. Now, moving on to this piece on purpose restrictions, right? So this is work that will appear next month at the Oakland Symposium, and it's joint work with my student Michael Schanz and Jeanette Wing at CMU. So purpose restrictions I've motivated before show up in a lot of privacy policies, and there are at least two kinds of purpose restrictions. There are the not for restrictions that say that information is not going to be used for a purpose, and the only for that say that we want to use information only for a certain purpose and potentially not for other things, right? So the goal is to really give a semantics to not for and only for purpose restrictions that is parametric in the purpose, information, and action, meaning that we want it to apply for all purposes, for all types of information and all types of actions. And then to provide an auditing algorithm once we have a sense of what it means. So let me try to give you a sense of how we arrive at the final notion by using this running example. So imagine that an X-ray is taken in a medical office. It's added to the medical record, and the medical record is then shipped to a diagnosis for diagnosis by a specialist who is a specialist in reading X-rays. And the policy says that medical records are only going to be used for diagnosis, right? So the question is this action for diagnosis or not? If it was not for diagnosis, then this is a violation of the policy. So how can we go about defining what it means for an action to be a purpose? So here's the first attempt. The first attempt is that we are going to say that an action is for a purpose if it is labeled as such. So whoever is sending out the message is going to label the action with a purpose. And an obvious problem is that it kind of begs the question, because how do we know that that labeling is correct? What is the basis for doing that labeling? The other problem is that one action can have different purposes depending upon context. So if I go back to this example, intuitively it appears that these two actions are for diagnosis, but imagine another send record action from up there that cannot be for diagnosis because this was an X-ray specialist and the X-ray wasn't even added to the medical record. So although these two actions are the same syntactically, they're both send records, one is for diagnosis and not the other, right? So these two appear to be for diagnosis and this is not for diagnosis. So actions cannot just labeling actions with purposes is not sufficient. The natural next step is to try and also, whether this action is for diagnosis or not depends on the state from which the action was done. So maybe we should take the state into account, which is very natural, right? So our formalization of purpose must also include states. Now, if I look at this example, it appears that these two actions are necessary and sufficient for achieving the purpose of diagnosis, whereas that one up there is not sufficient because no diagnosis is achieved, right? Okay.
Necessity seems obvious.
Not necessity.
Sufficiency is below.
Okay.
So suppose we go from correct state and we send, but send to somebody who is not a specialist and cannot possibly do diagnosis.
Right. So then it's not going to be sufficient for diagnosis. I'm going to say that this attempt 2, is that an action is for a purpose if it is necessary and sufficient as a part of a chain of actions for achieving the purpose. So if you send it to someone who's not a diagnosis, then he will violate this. That action could not be for the purpose because it wasn't sufficient. But now I have presented it only to say that this is not very great. So now I'll argue that necessary is too strong and sufficiency is both too strong and too weak in a specific sense. Right? So let's first look at necessity. So here's a slight modification of this example. Now you see neither of these actions are necessary because instead of sending to the first specialist, I could have sent to the second specialist and vice versa. So necessity is too strong. So instead we are going to use non-redundancy. So non-redundancy is necessity with respect to a fixed sequence of actions. So given a sequence of actions that reaches a goal state, an action in that sequence is non-redundant if removing that action from the sequence results in the goal state no longer being reached. So if I go back to this example, both of these actions are non-redundant because if I fix an execution like this one, if I remove this, then the purpose is no longer achieved. So non-redundancy is the weakening of necessity that we are going to try and work with, right? So the 10.3 now is an action is for a purpose if it is part of a sufficient and non-redundant chain of actions for achieving that purpose. And this actually coincides, it's a slight adaptation of the counterfactual definition of causality that people who have worked on the causality, philosophers and also computer scientists like Julia Pearl, have very similar notions of causality. Yes?
What if you send it to a specialist and the specialist says, I can't make a diagnosis?
Good. Next slide. So I have now said I've now argued why necessity is too strong, and we have to replace it by non-redundancy. The next part I want to argue that sufficiency is too strong, partly because of what you're saying, probabilistic outcomes. Right? It's too strong because of probabilistic outcomes, but also it's too weak in a certain sense because if you look at this picture, then you might have a more accurate diagnosis if you used one specialist versus another. And in that case, we would like the record to have gone to the right specialist rather than to the one who always does better, if we know that that person always does better. Right. But instead of saying always does better, you can also have an expectation over it, things like that, right? The other thing is exactly what you're saying. You may not always get a diagnosis, even if you did an action with the intention of getting a diagnosis because of probabilistic outcomes. So that's the difference between the adapted counterfactual definition of causality and what we are going to end up with. So there are at least two things that motivate our thesis, which will be based on planning. Because of probabilistic failures, we cannot require that a sequence of actions actually furthers a purpose. We can only require that the agent plans to perform actions to further the purpose. And quantitative purposes saying we require that the agent adopts the plan that optimizes the expected satisfaction of the purpose. So that leads us to the thesis that an action is for a purpose if the agent planned to perform the action while considering that purpose. So if the actions, or in other words, an action is for a purpose if it is part of a plan or part of an optimal plan for achieving that purpose. Now, having reduced the question of what it means for an action to be a purpose to this more concrete thing about planning, now we can hope for algorithms for checking.
I think if we speak about not for the purpose, that seems reasonable. But if we say only for a purpose, now it's very common, suppose I'm doing X-rays, to send to a specialist, which we work. So our purpose also, there is another purpose to increase our, be paid better.
Right.
To send to our specialist than outside.
Right. So good. So what you're getting at is that this algorithm is not going to be both sound and complete. It's going to be, let me try to think about this for a minute. It's going to be useful if it says not for an action is going to, so this is saying that an action is for a purpose if it is part of a plan for achieving the purpose. And if I show that the action could not have been part of a plan for achieving the purpose, all possible plans that you can think of given the environment model, then I know for sure that there was a violation. But I don't know that the policy was respected if I cannot argue that. So there will be a space of tenable deniability. And for not for a purpose, it'll be the other way around. Okay.
It seems, we all come from mathematical logic.
Yes.
And I think the logic appropriate here, more appropriate is the logic of chords, the logic of not making something true or false, but achieving beyond reasonable doubt or
I see.
lowering.
Yeah.
Lowering the.
Yeah, that's a very interesting point. So this is as far as we have gotten. I think we are presenting this as where we are after 2 years of thought. This is by no means the final word on this topic. So I'll be happy to hear about your thoughts in greater detail when we talk. And we haven't even gotten to a logic. We just have a model at the moment. We are wondering what the right logic for it will be. Initially, we were stuck for a long time on the counterfactual, the non-redundant but sufficient definition, which seemed very close to causality, and so all the work that has been done in that literature. But since we got to this planning, it seems a little bit different from what exists out there. So in the remaining few minutes, don't want to exceed the time, I want to give you a sense of what we did in terms of trying to get a sense of whether this hypothesis, this is our thesis, but is it true or not? What does that formally mean? What does it mean for an action to be for a purpose formally? And how do we audit for it, right? So for that first one, one obvious way is try little examples, which is what we did for 2 years before we got to this point. And the sequence that I showed you is a condensed summary of the kind of thought process that went into it. The other thing we tried to do was we gave a survey using this Mechanical Turk to about 200 people, and we compared the predictions of two hypotheses to provide responses to the provided responses. The planning hypothesis is ours, which says that an action is for a purpose if and only if that action is part of a plan for furthering the purpose. And the other hypothesis is an action is for a purpose if and only if that action furthers the purpose. So this was the current kind of reigning champion before this work. And the survey kind of overwhelmingly shows that at least those 200 people, cannot generalize too much from a sample of 200, but at least those 200 people, when there was disagreement between, we had 4 scenarios, one in which it satisfied both these hypotheses, and they said yes. A scenario in which both these hypotheses were false, and they said no. One in which this was true and this was false, and many more people said yes, and very few people said no. And when this was true and this was false, most people said no, and few people said yes. In the details of the survey, I don't have time to get into, but I have some backup slides at the end to show you the kind of questions that we asked them. Now, coming to auditing, the picture now is, in addition to the privacy policy and the audit log, there is an environment model for planning, which is essentially the state machine kind of thing that I was showing you, which formally is a Markov decision process, which is a standard model that is used in the planning community. So given a privacy policy, a Markov decision process that keeps track of the environment model, and an audit log, which records the actual execution, what actually happened, this algorithm comes back with obeyed, inconclusive, or violated. And the basic idea only for policies is that we want to find all strategies that are consistent with the observed agent behaviors under a model for the purpose P. And if none of these strategies optimize the purpose P under the model, then the agent violated only for P. And there is, this can be mapped to the Markov decision process, and the details I don't want to get into, but I'll show you an example on the next slide. The soundness theorem here is saying that the algorithm returns true if and only if the actions recorded in the log are not for the purpose. So if the algorithm returns true, you know that a not for purpose policy is satisfied, and an only for policy is violated. But the other side you don't know. There is tenable deniability on the other side. Now, if coming to this example, let me illustrate how the algorithm works. This is the Markov decision process. I've shown you states and actions, and there is the reward function. The reward function is essentially when you go from this state to this state, you get the difference in between these diagnosis scores. So you don't gain anything coming here, but if you go from here to here, you get 6, and here to here, you get 2. Right? So the optimal path through this model is this path. If any other path happened, then that would be a violation. So if you went on this path, for example, then this action was not for diagnosis, because it could not have been part of a plan, an optimal plan for achieving this purpose. Now, this can be algorithmically done using adaptations of plan recognition algorithms. Right? So this is where we are. Now, in terms of past approaches, while past approaches were useful, they were not semantically justified. So they included things like labeling actions or labeling sequences of actions or agent roles or code, but there was no justification for how the labeling should be done. So if the labeling was done incorrectly, then there wasn't any way of catching it. So our work provides a semantic foundation for these approaches that provides a basis for correct labeling, and the paper discusses in great detail some of the limitations. Now, in order to make this, so I'm not claiming that this work is usable as it currently exists. There's a bunch of reasons for that. Well, I guess one extension that we have worked out is enforcing purpose restrictions on information use. So what I was talking about so far is whether an action is for a purpose or not. But whether information is used for a purpose or not is a little bit more subtle, because there could be implicit flows. So suppose you want to say that gender will not be used for targeted advertising, then we have to show that the planning process is unaltered, whether you keep the gender as male or female. So it's similar to notions of non-interference and information flow. It's a combination of planning and information flow, if you will. Now, the other thing that gets in the way of making this approach, using this approach directly in practice, is we are assuming that these environment models, this Markov decision processes, are an input to this algorithm. But constructing them for complicated organizations is going to be a lot of work that we ideally don't want to do manually. So one of the things we would like to explore once we get the real audit logs is to see if we can learn these things from the logs. Right? And it's not out of the question, because there's a lot of work on Q learning and reinforcement learning that tries to learn Markov decision processes given observed data. Another thing here is, if you think about this model of planning, the reason we chose MDPs is because it's kind of the most developed formalism for planning in the AI community. But it's a good model of planning for things like robots, where you can program them to act in certain ways. People, not so much, right? It's assuming that people are completely rational and they can do all these complicated calculations. So if the AI community comes up with better models of human planning, then we could instantiate this framework with other models. However, I should say that although this is not such a great model for human planning, it is something that an organization could use to analyze this environment model and prescribe more operational policies for humans, where the calculation is done by the organization, not by humans. And finally, we really want to push on applying it to practice. So as we get the audit logs from the Sharps project from Northwestern Memorial and Johns Hopkins and Vanderbilt, that's the next thing on our agenda to try and apply this. So I'll leave you with this picture of how audit works, and is separated into auditing for these black and white concepts and gray concepts like purposes, and the final kind of big picture of using audit and accountability for enforcement. Thank you very much. I'm happy to take these. Yeah.
Since we looked into HIPAA, what is your impression? How well it's written? So suppose they would consult computer scientists.
Right. So HIPAA was very operational. So that was one very good thing about HIPAA. And that's part of the reason why the first algorithm that I presented was quite effective for big chunks of especially for disclosure. Conditions under which disclosure can happen is very operational. Now, the other thing, that the specific question that you had asked earlier about one thing having higher priority over another, that was also spelled out quite explicitly. The structure of the clauses, I can use the board, was often of the form that so there were a bunch of what we were calling positive positive clauses. And there was a conjunction over these positive clauses. So all of these conditions are negative clauses, whatever we're calling them. I think we are calling them negative clauses. All of these policies have to hold. All of these clauses have to always hold. And then there were a bunch of positive clauses that said if any one of these held, it was okay to share information. So one way to think about this is these are saying under these conditions it's okay to share information, and these are saying it's a generalization of the denying clauses that unless these things are satisfied, you cannot share information. Now, the interesting thing about the way the law was structured is that the positive clauses had conjunctive exceptions, and the negative clauses had disjunctive exceptions, right? Meaning that this condition has to be always satisfied except if this other thing happens, which means that this can be written as a negative core or an exception. And these had conjunctive exceptions, meaning that if this holds, you can release information to this third party, except if this other thing also holds. So these had like a core with a conjunctive. And so the preemption mechanism, the priority mechanism, was encoded. When we tried to formalize it, this is what it looked like in the logic. And you could imagine multiple nestings of these kinds of exceptions, but in HIPAA there was only one level deep.
Maybe it comes from these languages used in law, when you write laws.
Right. Yeah. So if you have, I guess I'll talk with you in greater detail. If you have suggestions about, we are using first order logic, right? But you could imagine using better logics that are more suited for this application. That will, because of these exceptions, and they're encoding in this manner, the formulas get a lot bigger, right? I know that Insoup Lee tried to do something with deontic logics, but for a very different application. So I don't know what other logics might be suitable here, but that would be an interesting conversation to have. Yes?
So in general, the English in the laws is fairly unambiguous? Or
yeah, I think most of the, well, it required a clever CMU grad student. The formalization took over a year to do, but Henry was also doing other things with Frank Fenning. But there were only a couple of places where we had to go talk to a lawyer. And the lawyers came back with some answers that helped us a little bit. But I don't want to claim that this is an authoritative encoding of the law. I think we have to make these things open source and up for discussion and debate. We do need input from lawyers, but for the most part, the high-level bit here is HIPAA is largely operational, and that's actually the way the law should be written. The places where it's more abstract are things that have to do with purposes and beliefs. But at some level, that seems like the right level of abstraction, because how are you going to, unless you say that personal health information can be shared for the purpose of payment, treatment, and operations, if you try to make it more operational, then you have to list all the conditions. And that seems like it'll vary from organization to organization, right? So I wouldn't know how to make it more operational. On the other hand, what will impede, one other thing that will impede these kinds of techniques to be applied, if there are lots and lots of laws and policies, is you will need a Henry de Jong for every one of those laws and policies, right? So if it could be written in a more structured, if we can figure out an input language that is more structured while being more usable, so that it's not first order logic or some other complicated logic, that could then serve as a way for an automatic compilation That would be, I don't know that it'll ever happen with laws. It's interesting. I gave this talk, and Michelle Denedy, who is now the Chief Privacy Officer of McAfee, but was at Sun and Oracle before that, she got very excited. She went to Washington and tried to convince the senators to write in their laws in some structured language. And she didn't get very far, unsurprisingly. But maybe that's something that companies can do, right? A company like Microsoft, if they have a usable way of writing policies, that could then be used to compile down to something that an enforcement engine could operate on. That seems much more doable. Because what gets ultimately enforced in an organization is not the law, because the law tends to be more abstract. But internally, the policies tend to be more operational. So yesterday, when I was talking with the chief, with the corporate privacy people here, that's one thing that we discussed we might want to do. Look at the internal privacy policy and see if they're working on making it more operational, apparently, right now. See if we can work with that, right? Yeah.
Can you give us an example of one of the places where you had to talk to a lawyer?
Oh, I will have to look up my email. It's been, the formalization was done about 3 years ago, so I don't remember, but I'll dig it up and let you know. Yeah. I have no memory of it anymore. I've blissfully forgotten. Right.
Thank you.
Thanks.